Okay, so now that we have that figured out, now let's figure out how you're going to apply it. So I get a mass of 1.02 kilograms, about like yay. I'm going to put an inclined plane. First thing I want to do is calculate force parallel, force normal, and my gravitational force. If you can't do that, you are dead in the water at this point, okay? So, my force parallel, and make sure that you are not in radian mode on your calculator. You have to be in degree mode. So your force parallel is just going to be Fg sine theta. So that's going to be 10 newtons times the sine of 30 degrees. Trust me on this one, you're going to get 5.00 newtons because the sine of 30 is 0.5. Okay? Now, here's the decision that you want to make. Okay? Caitlin, in your world, do you want the force parallel, which is acting down the inclined plane, to be a positive or negative number?
Negative.
Negative. Okay. So in Caitlin's world, on an XY system, anything going down is going to be a negative value. Okay? Anything going down is going to be negative. Anything pointing up is going to be a positive value. Now, Vanessa might go, hey, I want downhill to be positive. Cool. There is no right or wrong way to define the system. But once you define the system and you start working a problem, you have to be consistent with that system. So if we're going to go off Caitlin's system, downhill is going to be negative. That's going to be a negative 5 newtons. Okay? If Vanessa had said, no, Mrs. Burkhead, I want downhill to be positive, I would have made downhill be a positive number, and that would have been positive 5. There's no right or wrong way to do this. Okay? But once you start within a problem, you can't change it. Now, you get to the next problem, you go, oh, that didn't work out. On the next problem, I want downhill to be positive. Fine, you can do that. But within the context of a problem, once you start down that road, you have to stay with who took you to the dance. Okay? Now, next thing I need is my normal force. So somebody get a calculator. This one I don't know off the top of my head. So somebody take 10 newtons times the cosine of 30 degrees. It's 8 something.
8.66.
8.66 newtons. Okay? So that's going to be 8.66 newtons. My force parallel is negative 5. Okay, so that's our bedrock. Okay? Now we have our numbers. So now we're going to begin to play with this in terms of how it works with problems. So here's the first problem. I would ask you, what's the acceleration of a 1.02 kilogram mass sitting on a 30-degree angle, and there is no friction? Okay? So, you're like this. You're at a 30-degree angle, like this, okay, which is about like it. I'm going to put this on here. I'm going to let go of it. I want to know what the acceleration is going to be. Now, based upon this graph that we drew up here, so here's like 30 degrees. What is my acceleration? Between what two numbers does my acceleration have to be?
0 and 9.8.
Between 0 and 9.8. Okay? That's where my acceleration has to be, between 0 and 9.8. If I get an acceleration bigger than 9.8, ooh, that's weird. Okay? If I get an acceleration less than 0, that's even weirder. But it's going to be somewhere in that range, somewhere between 0 and 9.8, because I'm on an incline. Okay. Now, what I would highly recommend is that you do the chart thing. Now, the chart's going to be a little bit more complicated now. Because now we can have force applied, we can have force opposing, but now we can have force parallel, which we didn't have to worry about before. Okay, before it was just force applied and force opposing. But now we have force parallel in the mix. But that's still going to equal the net force. which is still gonna be the sum of all the forces, and that's still gonna equal mass times acceleration. So the only difference is that now we're gonna have a third column, or third row in our chart. So, was there any applied force? No, I set the cart on there, I let go of it. My applied force is 0. It's a frictionless surface, so there's no squirrels, there's no fans, nothing. My opposing force is still 0. Do I have a force parallel?
Yes.
And we're in Caitlin's world, and we said that was -5 newtons. Now, by virtue of the fact that I'm asking you to find an acceleration, what is your net force not going to equal? 0, okay? So as soon as you say, hey, what's the acceleration? Net force can't equal 0. So, oddly enough, if I add all those together, I get -5 newtons. Cool. That's the only force acting on it. So when I have this inclined planes, so when I have this at a 30-degree angle, and I let go of it, there is only one force, and one force only, that's making that cart move down the inclined plane. There's nothing else. That's it. So now to get my acceleration, so somebody take -5 newtons and divide that by 1.02 kilograms.
Negative 4.9.
-4.90 meters per. That matches, right? We said it was going to be somewhere between 0 and -9.8. We're at -4.9. Cool. Okay? Simple. Now I want to change the problem. Now I want to know how much force okay? So now we're going to change it. I'm still going to have the 30-degree angle. Still got my cart. But now I want the cart to go up the hill at a constant velocity. What are the two most important words in that problem? What'd you say? Constant velocity. So what is your net force going to equal? 0. Now, draw this out. Here's my inclined plane. Here's my box. Here's my FG. There's my force parallel, -5 newtons. There's my force normal. So obviously if I'm going to push it up the hill, Gavin's out knowing he has to push the motor up the hill. Which direction are you going to push, Gavin? Dylan, sorry. Dylan is pushing, Dylan is mowing. Which direction are you going to push the mower?
Up the hill.
Up the hill. So, Dylan wants to push the mower up the hill at a constant velocity. So if there's a downward force of -5 newtons, which is basically the frictional mafia, the gravitational mafia. So the gravity mafia is going down at -5. How much applied force do you have to apply? 5?
More than 5.
No, just 5. So if you set up your chart, again, force applied, force opposing, force parallel, and force net. So there's still no friction, so we don't have to worry about that. Okay, we have not introduced friction into the system. My force parallel, because we're still working in Caitlin's world, is -5. Okay? So what has to be the value of my applied force?
5.
+5 newtons. So that everything adds up to
0.
0. Okay? Go with that.
Yeah.
Why
Got
are
it.
why are we just ignoring the force natural and force gravity? Like, why does it not affect?
Oh, no, it is, okay? So, the reason that we don't worry about the normal force is
Mhm.
because that's acting up like this. That's not impeding the motion,
Okay.
okay? So this is kind of like what happens in the X stays in the X, and what happens in the Y stays in the Y.
Even though like force normal and force gravity don't add up to 0, it doesn't matter.
Doesn't matter, because the only acceleration or forces are gonna be acting that, in that line of motion. Are they there? Yes, okay? But doesn't matter. It's just like, if I push this thing along the table, gravity and normal are there, but that doesn't affect my horizontal motion. So those forces are very much there, but we only worry about the forces that have the capacity to impact the motion of the object. So that force parallel is just a subset of that gravitational force. So it's just a part of that 10 newtons that's acting down the inclined plane. That's where we take it into effect. And the normal force, that's just keeping it from falling down,
Okay.
okay? So that's why on your chart, never throw in force normal. Never throw in gravitational force, okay? Because the gravitational force is taken into account as your force parallel,
Okay.
okay?
Mhm.
Makes sense.
Yeah.
Okay. Situation number 3. I'm going to let go of the box of the cart. But mu is 0.150. Find the force friction, the net force, and the acceleration. Okay? So, instead of having it like this, where you've got the wheels like that, basically a friction to the surface, now I'm going to do it like this. Now there's friction. But before you do any math at all, think this through in terms of your diagram. So you still have the trifecta. You still have your gravitational force, you still have your force parallel, you still have your force normal. Okay? Those three will always be there. They never go away. Always, if I ask you to draw forces on an inclined plane, and I'm going to, you always have to have those three. There is no situation where you are not going to have those three. Okay? Now, I let go. Which direction did the cart accelerate? Down. So which direction is my net force going to be?
Down.
Down. So if I set up this chart, force applied, force opposing, force parallel, force net. When I let go of it, clearly which direction did it accelerate?
Down.
So what's going to be the sign of my net force?
Negative.
Negative. So my net force has to be a negative value because that's the direction of the acceleration, and Caitlin said she wanted down to be negative. Okay? So when I get done, I know I'm going to have a negative net force. What's going to be the sign of my acceleration? Negative, because that's the sign of my net force, right? Okay? Cool. So if there's friction, is that going to alter my force parallel? Yay or nay?
No.
Absolutely not. How do you calculate force parallel?
Force
FG
gravity
sine theta.
times
When you look at how you calculate force parallel equaling Fg sine theta, is there any way at all to introduce into that equation the coefficient of friction? Nope. Whether there's friction or not doesn't make any difference. Your force parallel is just Fg sine theta. That's all you've got. Okay? Friction does not impact that value. Boom, that's what you got. Now, look at how you calculate force friction. So force friction, however,
It's force normal.
is mu times force normal. Woo, okay? Now, this is where you're going to use the force normal part of this equation. Here's the most common mistake that's made. Mark my words. As you go, oh, this thing weighs 10 newtons, and I'm just going to put 10 newtons in for my force normal. Okay? No bueno. Why?
Because force normal is
Yeah. Does it weigh 10 newtons? Yes. Is the normal force 10 newtons? No. So this is where you've got to use that FG cosine theta part. This is where the cosine theta part now becomes a big deal. So we said that the normal force is what,
6.6.
8.66?
Mm-hmm.
That's going to be 8.66 newtons. So now, to get my force friction, I'm going to take 0.15 times 8.6. So somebody, oh, you take 0.15 times 8.66.
8.66.
What'd you get?
1.3.
1.3 exactly?
1.30.
1.30 newtons. So here's an odd situation. This is where the frictional mafia and the gravitational mafia are actually like fighting each other. Okay, so this is the one situation where this is a battleground between the two of them. So you've got the gravity mafia, which is wanting it to go down the hill at -5. The frictional mafia is going, whoa, 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 boys, boys, boys. The frictional mafia, remember, always acts in the opposite direction of motion. So the gravity mafia is trying to slide this thing down the hill. The frictional mafia is going, hey, whoa, 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 we don't want to, no. We don't want you to go. So that force friction was what, 1.30? So who's going to win? The gravity mafia or the frictional mafia?
Gravity.
Gravity, because that's bigger, right? So on your chart, the force applied is still 0. We're not pushing it. We just let it go. We're not pushing it. My force opposing was 1.30 newtons. My force parallel was -5 newtons. Oh, this makes sense, because now I end up with a negative net force, and that's what we said should happen. So if I do this, I get, check my math, 3.0
7.
newtons. So somebody take -3.7 and divide that by 1.02 kilograms.
-3.627.
-3.63. Now, what's happened to my acceleration when there's friction?
Lower.
It's lower. Why?
Because you're fighting friction.
Yeah, you're losing some of that force parallel to overcoming friction. That would be like if you've ever gone skiing, this is like trying to ski with like sandpaper on the bottom of your skis, okay? Gravity's still trying to pull you down, but now you have this massive frictional force acting in the opposite direction. Okay, so here's the last problem, and then we're done. The good news is we don't have to recalculate anything. So how much force is needed to pull it up the hill with Jack and Jill at constant velocity if mu equals 0.13, no, 0.15. What are the two most important words?
Civil velocity.
Net force is going to equal?
0.
So, start with the diagram. You're going to have Fg, force parallel, force normal. Dylan is pushing the mower up the hill, but now there's friction. Dylan, which direction are you going to push the mower?
Up the hill.
So the force applied is going to be going up the hill, right? The mower is going up the hill. Which direction is force parallel going to act?
Down.
Always down. Force parallel always acts down the hill. But which direction is force friction going to act?
Up the hill.
Down,
Up the hill.
down,
Down the hill.
down.
Motion.
Because we're going
Down the
Yeah,
hill.
down.
Why?
Because
Because
we're
you're
going
going
up.
up
Which direction does friction always act?
the opposite.
Opposite of
Opposite
the
direction of motion. So I'm pushing this thing up the hill like this. So which two forces do I have to overcome?
Force parallel and
Force parallel and
force friction.
force friction. So now that's going to be acting down the hill. So because we decided to make this negative, my force parallel is negative 5 newtons. My force friction is now going to be
Negative.
negative 1.3 newtons. So if you set up a chart, highly recommend, force applied, force opposing, force parallel, force net. What do you want the net force to equal?
0.
So my force opposing was negative 1.3. My force parallel was negative 5. Therefore, my applied force has to be 6.3 newtons. Okay? That's as complicated as it gets. So, keep that going. I need to hand out the assignment.
I think it's okay if you don't find it.
Ooh, color paper.
Yeah, that one's on colored.
Why do you have 3 different colors?
Oh, it's on
Papers?
orange.
Ooh, these are nice colors. Do the colors mean anything? We get
Huh?
Do the colors mean anything?
I'm not that organized. Okay, so on 1 and 2, all you're doing is just calculations. Again, make sure you are not in radian mode, or you're going to get answers that make no sense. When you get to question number 4, you're going to take a 1.2 kilogram box, 20-degree hill. In your system, uphill is defined as positive or negative, and downhill is defined as whatever. I don't care how you set up your system. Make downhill negative, make downhill positive. I don't care. But once you set up that system, you have to stick with it throughout the entirety of this problem. Not through the entirety of the worksheet, but through the entirety of that problem. Okay? Gavin?
Is number 4 worth a point?
Yes. Now, so what I'm asking you in number 5, what is the force parallel that is acting to accelerate the box down the hill? So, over here, I've given you
An angle.
the outline.
Yeah.
What are the forces acting on, you don't have to draw this to scale, but what are the forces acting on the system? Force normal, which is going to be acting not straight up, but at a 90-degree angle to the incline. That's one. What are the other two?
Force gravity, which is straight.
Gravity, which is straight down,
Force parallel.
and then your force parallel. At a minimum, on every time you see a triangle for those forces, that inclined plane, those are the 3 that you always have to have. Okay? So, then yes, there is the backside, but do all the work on here, do all the diagrams on here. Okay? All right. We're good.
Wait, so we do all the work on this one, and then do all the